Picture this red line as the top-down view of a plane that dissects the Earth and the Sun. In the heliocentric model, the Moon passes this plane twice per orbit. When it passes the plane on the Sun side, it is a new moon. And when the Moon is perfectly dissected by the plane, it is peak new moon, the moment when Sun, Earth, and Moon are perfectly aligned on that plane. When it passes the plane opposite of the Sun, it is a full moon. And when the Moon is perfectly dissected by the plane on that side, it is peak full moon, the moment when Sun, Earth, and Moon are perfectly aligned on that plane. According to the astronomy department at Cornell College, at full moon, the Moon rises at sunset and sets at sunrise. Of course, this is also according to any astronomy department in any university. It's also according to Stellarium, Starry Night, and every other astronomy software out there, since it's a basic tenet of the heliocentric model. Here's a real-world example of that on March 20th, 2019, a little bit west of where I live in Tonopah, Arizona. We had a full moon that was going to be peak full at 6:42, and the Moon rose at 6:35, and the Sun set at 6:43. So we're going to have peak full moon rising as the Sun was setting. I went out to photograph it. Unfortunately, really bad weather and an ill-placed mountain messed up my plans, but we can still see the same thing on Stellarium. Tonopah was a little bit west of where my standard location of Mesa, Arizona is, and to make everything easier, what I'm going to do is I'm going to keep the same longitude but bring it down to the equator. So I'm going to change this to 0, and Tonopah is a little bit west. I'm going to change that to 112. Okay, so that gets us there. We're going to be UTC -7. Okay, and then I'll just find the date, which was what, 320? About 8:42, or I'm sorry, 6:42. Okay, so right here you can see the Moon is getting ready to rise in the east. Sun is just setting right at the time of peak full moon. Now, if I go to the antipode of this location, the exact opposite side on the ball Earth, then we'll see the opposite. We'll see the Sun about to rise in the east as the Moon sets. Same time and everything. So let's see, 1842. So on the other side of the Earth, it's actually going to be 321 at 6:42 in the morning. But let me do that. So we'll keep it at on the equator, except for we're going to be 180 degrees opposite this, so we're going to change that to 68 degrees east. So 68 and east, and this will be +5 UTC because we are exactly 12 hours difference from the -7 that we were at the first location. So alright, and it automatically changed it to the 21 at 6:42. But see, now we just see the opposite of that. We got the Moon setting in the west as the Sun rises. And that's how we're told the heliocentric model works for full moons. Two people on opposite sides of the Earth, both at the terminator line, can see both Sun and Moon at the same time simply by turning around. One sees the Moon rise as the Sun sets, and the other sees the Sun rise as the Moon sets. The problem with this is that in the helical model, the Sun is 400 times farther away than the Moon is. So if our Stellarium guy could only see the top of the Sun rising because the horizon was blocking the bottom of it, how can he then turn around and also see the top of the Moon when the angle to the Moon is so much steeper due to it being 400 times closer to him? And yes, I realize that this diagram isn't to the scale the ball Earth is made up out of thin air, but surely you must realize that if the hypotenuse of one right triangle is 400 times longer than the other, these acute angles are going to be very different. This problem becomes easier to visualize when the moon is at peak new. Again, from Cornell College Astronomy Department. At new, the moon rises at sunrise and sets at sunset. Of course, that's got to be the case in the helical model, right? Because if our stellarium guy can see half of the sun here and turn around and also see half of the moon here at the same time, then he's got to be able to see half of the sun and half of the moon at the same time here. Because the only thing that has changed is that the moon is now on the sun side of the Earth. The distance from Mr. Stellarium to the moon hasn't changed at all, which means his angle to the moon hasn't changed either. And of course his angle to the sun is identical to what it was before, right? So does the new moon alignment make it easier to see the problem? How can Mr. Stellarium see the new moon rise with the sun if the two objects are at very different angles? So I tried to find a new moon rising with the sun, and I found this month on the 5th in Perth, Australia. We got peak new moon at 6:45, moon rise 6:49 within 4 minutes, and sunrise 6:50. So everything within 5 minutes. And so I got that up on Stellarium to see what that looks like. So I'm going to just back it up a little bit. But this, you can see this is Perth on the 5th and right before sun/new moon rise. And you see them both rising together, just like earlier we saw the full moon set as the sun rose and rise as the sun set. On new moon, it's just the opposite alignment of that. They rise and set together. I looked around and I found a place called Pontianak in Indonesia. And the same date, May 19th, the 5th, we've got a new moon at 5:45 a.m. right as it's rising. Right there, okay, that's Pontianak. Now, and I've got the date set up already, but Pontianak is right on the equator. It's only less than 2 minutes south. So what I'm going to do just to even things out, I'm just going to make it 0, and it's 109 and 19 and a half minutes east. I'm just going to make it 109 even. And then I just went the opposite of that. I went on the equator again, and then I went 71 west to be 180 degrees away from there. Also, I didn't point out that Pontianak is UTC +7. So on this other screen, I did UTC -5. Okay, but it is also right on the equator and 71 west as compared to Pontiac. So the antipode. And this is May 4th at 5 o'clock in the evening, which coincides with Pontiac's May 5th at 5 in the morning. Let me put it down to 0. Alright, so they're both 5 o'clock. Basically 5 o'clock in the evening, 5 o'clock in the morning, but they're happening at exactly the same time on Earth. It's just our time zones that change. But these things are happening. So if I let this run, you can see sun and moon getting ready to set together. Not exactly, but pretty close. So there's sun and moon setting. Now during that same time frame over here, we'll have that sun and moon that just set on the left rising over here. Again, not exactly. They're not 100% aligned. But according to timeanddate.com, the peak full moon was at 5:45. So that's right there. Let me put this one back to 5:45. Okay, so this is the precise moment in time. Just two people on opposite sides of the earth. One's looking east, watching sun and moon rise. One's looking west, watching sun and moon set. Okay, same moment in time. Here's how that last stellarium example looks on this diagram. We have the guy at 5:45 p.m. seeing the sun and new moon set together, while the guy at 5:45 a.m. saw them rise together. How in the world can they see both of them at the same time? Maybe you'll say that they didn't rise and set exactly together, but were a little offset. Okay, but if we offset the moon so that the PM guy can see them setting very close together, it only makes the AM guy's angle even more impossible. Besides, I set the time to when timeanddate.com said the sun, earth, and moon were all perfectly dissected by my red plane, right? And keep in mind that I just picked Perth and Pontiac because timeanddate.com makes you choose a fairly large city, and they were very close to the event I wanted you to see. But rest assured, on any given full moon, there will always be a place on Earth where you can see the moon rise as the sun sets, and at the same exact moment in time, another place on Earth where you can see the sun rise as the moon sets. Likewise, during every new moon, there will always be a place on Earth where sun and moon rise together, and at the same exact moment in time, another place on Earth where they are setting together. It can be no other way in the model they've given us. I've got more to say on this subject, like how this works for solar and lunar eclipses, but I'm going to end this video with a cheesy little demonstration I did at home. Rich and I are going to do another one on a much larger scale, but so far time and schedules have not permitted. So in the meantime, maybe this cheesy one will help you to get your head around what I'm saying. Thanks for watching. Okay, this is my cheesy little new moon experiment. Rich and I have been planning a grander scale experiment, but our schedules just haven't worked out timing-wise to do it yet. But we will be doing it. This 4-inch diameter ball, that is the Earth. Okay, and you can hopefully see that's 4 inches in diameter. I've got it 10 feet away from this rail, and it's the rail that I put this little, I don't know if you can see it here now because of the backlighting, but there you go, Christie's tape on it. So that's the rail we're going to be using. That's the one we're measuring from. So 10 feet away. The reason is because my Earth is 4 inches in diameter. The rail is 1 inch. So that is a quarter of the diameter, same as the moon is to the Earth, we're told. And the moon is 30 Earth diameters away from the Earth. So 30 times 4 inches is 120 inches, which is 10 feet. And that's why I've got it set at 10 feet. Okay, this is the camera that I got it on its side because I want it to look like this as you're coming around the side of the Earth. It's like you're standing on your side. Like right now, your feet would be touching the Earth on the terminator line on the equator, and your head would be to the left. Your head would be, towards the yellow tape. All right, so when I'm going like this, it's like the sun or moon is rising up. And I'm going to go the other way too, so coming this way, it'll be like the sun and moon is rising for someone on the other side of the ball that's standing upside down to the first person. Okay, in the background here is a palm tree right there. Now it is 40 times the diameter of the moon, not 400. Okay, I can't quite do the 400 right here. At least not that I know. So it's 40 times the diameter, and it's 40 times as far away. So when I line the camera up on them, they look identical in angular size. Okay, so remember it's 40, not 400. 40 times as wide, 40 times farther away. That actually works in the ball's favor, because the farther I put that sun out, the worse this effect is going to be. So now I'm going to get on this camera, and you will see from there what I'm going to do. I'm basically just going to slide it left and right, keeping it as parallel to that rail as I can. You know, I don't want to be tipping it. I don't want to be turning it, you know, this way, cocking it. I'm going to try to just do a straight line by. So you're standing on this side of the earth, and then a straight line back. You're standing on this side of the earth, just keeping it parallel. Okay. Okay, so now I'm taking over with the P1000. First thing I'm going to do is get our earth out of the way. And I'm going to zoom in. Let's find the one. Well, we know it's this one with the piece of tape on it right here, because it's next to the tape measure. So here I am. You can see the palm tree in the back. See it over there? I'm just tipping the camera a little bit. It's the same. Let me go off to the side a little bit here. There we go. Same angular size. Especially that fatter part at the top. Basically the same angular size. See there? As the pole. Or as the bar. Okay, so now I'm going to line these up perfectly, because that is new moon alignment. The sun, the center of the earth, and the moon are all directly aligned. So now I'm going to bring my earth in at its 10-foot distance. I'm going to move this tape though. So I'm just rolling the earth in. And I've got the earth, let me back up a little bit. Okay, so I've held the camera in the same place. So the earth is centered on the moon, which is centered on the sun. Sorry about that, I had to get that tape out of there. Okay, so now I'm just going to slide the camera straight left. I'm not going to, you know, cock it anyway. I'm just going to do horizontal slide. Okay. The lighting all got bad because I'm... Okay, so now what we're trying to do is, as I approach the equator, okay, remember the side of the ball is the equator, and I'm standing with my feet right touching the ball. This is you standing right side up on the equator at the terminator line, watching the sun and moon rise on your horizon. Do you see what I see there in the background? I see that fat tree. Okay, I'm seeing the sun first because it is much farther away. Now I've got to like jump in an airplane or jump on a hot air balloon and rise myself up. Hey, stop zooming. I've got to rise myself up to see that bar, and it's the bar. It is the bar that's just now touching the earth. I don't know if we can see that tape because of the bad lighting here, but okay, but this is what I wanted to show. Okay, looking at the horizon, the first thing that's going to come up over your horizon is the sun. Then, while the sun is up in the air, the moon will come up. So sun setting right now, or let's just say rising. Sun is rising right now. After the sun clears the horizon, gets up in the sky a little bit, now we can have the moon actually on the horizon. We cannot have them both on the horizon at the same time when they are in syzygy, when they are directly aligned with the center of the earth. Now I'm going to do the same thing. I'm just going to go to the other side here. So now I'm just trying to keep it straight how it was. Okay, and there's our tree already. So on the other side, so right now that tree is the sun rising or setting on the horizon. Doesn't matter which way you want to look at it. Well, since I'm going this way, we'll say it's rising. So sun is rising on the horizon. Sun is up in the air. And now, there's our moon, that bar right there. So we finally got our, look how far the sun is up in the sky, you know, before we even see the moon. Alright, and same thing setting. So now, as it's setting, the moon is going to set first while the sun is still up in the air. And then a while later, now we got the sun setting on the horizon. Okay, I know this is a cheesy experiment, but I hope you get the idea. It's like a parallax type thing. The farther away the distant object is, I went way too far. There's that sun. There's the moon. Sun. That bar is the moon. The one that's touching the horizon right now. They can never be, if they're in a straight line centered with the Earth, nobody on the side of the Earth can see them rise at the same time.